That's a good-looking guy.
I was going to say dark, tall, dark, and handsome. And of course, most of our interactions over a span of nearly 30 years have concerned foundations of quantum mechanics and things like this, kinds of things we saw in the last talk. And although I never had the pleasure of collaborating with Basil, I have collaborated with 4 of the Prof Hiley Mafia, by which I mean their graduate students. 2 of them are here today. And it was a very enjoyable part of my career. And this was done in the attempt to understand better the ontology of the de Broglie pilot theory. And I do very much congratulate Basil for his work in this area. And I do very much reinforce what Chris just said. You may like or dislike, you may believe or disbelieve the Broglie picture of quantum mechanics, but it is a wonderful antidote to dogmatism. And we teach it every year in Oxford in our degree in physics and philosophy. Of course, Basil's interests are much wider. He's interested in space-time, the difference between pre-space and space, as understood in the context of the implicate and explicit order distinction. What I was going to do today was to talk a little bit about general relativity, something I've become interested in recent years. My comments today are going to be about elementary things in general relativity. This is what happens when you invite a philosopher of physics. Nothing is obvious to us, particularly the obvious things. And I should say that my comments are based on discussions I've been having with James Reed, who's a graduate student in philosophy at Oxford, and with Dennis Lemkel, who's an Einstein expert at Caltech. So I'll start with remarks on the weak equivalence principle, and then the strong equivalence principle. Of course, the weak equivalence principle has really 2 roles in textbooks. One is a kind of heuristic role. How do you make progress in understanding gravity when you don't have a theory of gravity, but you're in the special relativistic context? In special relativity, you don't have a theory of gravity. Well, in special relativity, the only theory of gravity you have is Newtonian mechanics, and that's clearly not Lorentz covariant. So effectively, you don't have a theory of gravity. How do you make any kind of progress whatsoever? How do you find your way to a theory of gravity? But of course, it also has a role in general relativity itself. It's supposed to be buttressing some fundamental intuition that we have in general relativity. So I'll say more about the latter aspect. How to understand the weak equivalence principle in general relativity as opposed to using it as a heuristic principle, which of course Einstein did. And then I'll say something about the strong equivalence principle. I'm not going to go through all the so-called equivalence principles. This is the one which has to do with the local validity of special relativity and general relativity. And I'll try to say how, for me, there's something rather mysterious about this in general relativity. In 1907, so this is 2 years after Einstein had published Special Relativity, of course he was thinking about gravity, and as many of you know, some years later he said, in 1907, I think when he was working at the patent office in Bern, he said to him, he had the happiest moment of his life. He was imagining an unfortunate man falling off the roof of his house. And as this man fell to the floor, this man realized that all the objects around him in similar free fall looked as if there was no gravity acting. So in other words, you can transform gravity away by a suitable state of motion, free fall. When you think about this, you say to yourself, well, so what? I mean, anybody that's familiar with Newtonian gravity would know this. One only has to think of the application that Newton made of his corollary 6 in the Principia. When, for example, he was talking about the dynamics of Jupiter's moons, he pointed out it didn't matter when you were analyzing Jupiter's moons in the Jupiter system, you could ignore the fact that it was actually falling freely with respect to the sun. So this happiest thought of Einstein's life is in a sense banal in standard theories, and certainly Newtonian gravity. But of course, Einstein put a twist on it. Here was what the happy thought was. You can transform gravity away. Now, what does that remind you of? Well, 2 years earlier, one of the fundamental insights he had in developing special relativity is that you can do something similar with electric and magnetic fields. They are coordinate dependent. You can have situations where a field appears in one coordinate system, but with respect to a boosted coordinate system, that field can disappear. Einstein saw Maxwell's theory as the first unified field theory, in the sense that you were introducing two different kinds of fields, but in some sense of the word, the totality, they were unified. To call them equivalent seems to be a misnomer. You don't say the electric and magnetic fields are equivalent. You say they're two parts of a bigger story, and each one is frame dependent. And Einstein suddenly realized maybe it's the same as inertia and gravity. Maybe inertia and gravity are like the electric and magnetic fields. They're not equivalent, but they're part of a unified story. So here's what he says in 1920 in a paper in Nature. He's thinking, for example, of an observer observing some system that's in rotation, and the observer is seeing these inertial forces arise, and then thinking what it would be like to be sitting on that rotating body. And so he says the same property which is regarded as inertia, or an inertial force, something like the centrifugal force, from the point of view of an inertial system not taking part in the rotation, can be interpreted as a gravitation when regarded with respect to a system that shares the rotation. Different frames, different description. Inertial frames, you describe certain things in terms of inertia, inertial forces. In non-inertial frames, you introduce a gravitational description. So this is the essential point of Einstein's happiest thought. It reminds him of the origins of special relativity in relation to his understanding of electric and magnetic fields. The problem was that in Newtonian mechanics, when we talk about something being an inertial force, we don't regard that force as something real. We regard it as simply, inertial forces are not real forces, they're simply a result of the first law of motion, a result of the fact that force-free bodies tend to move in straight lines at uniform speeds. You don't have to introduce Newtonian forces to account for the centrifugal force. In that sense, that somehow they don't have the same reality as other forces. Einstein thought gravity was a real force, so Einstein said we have to abandon Newtonian mechanics in some sense. We have to come up with a new theory of gravity. Well, of course, in a sense, the rest is history. This week, we're celebrating the first publication, public announcement of Einstein's field equations, 1915, or this very week. I'm not going to go through the history of that, which is fascinating in and of itself. And by the way, with his tremendous battle with Mach's principle and how eventually he had to give it up, and how it misled him in various ways, and he reinterpreted it in various ways. But I was struck, by the way, by the fact that when people were referring to past thinkers as justifying some notion of an individual holism for the universe, nobody mentioned Mach. And this really was one of the most fundamental features of his thinking. He saw the universe as an indivisible whole. But let's assume then we know the story of how Einstein got his field equations. But now, Einstein saw general relativity, after he developed the field equations, as the second unified field theory. And here you can see it directly. There's a very nice paper, by the way, by Dennis Lim on this aspect of Einstein's thinking, which is often overlooked in the literature. Here is the geodesic equation. Now, Einstein, in 1915, 1916, and until sometime later, assumed that a test body, the trajectory, the world line of a test body would correspond to a time like geodesic. This was an assumption that he made. It was a postulate. And here's the equation for the geodesic, and it is clearly coordinate dependent. Because here is the Christoffel symbol related to the affine connection. Of course, it's the connection that's compatible with the metric. You can always choose, for a given event in spacetime, you can choose a coordinate system in which that thing vanishes. So now you're left with an equation that looks as if you're saying that the acceleration of a body is zero. That's Newton's first law of motion. So this thing represents gravity. Throughout his life, Einstein said it was the affine connection that represents the gravitational field, not the metric field. But it's clearly coordinate dependent. In other words, in some frames you can turn gravity off, in exactly the way that is the case with electromagnetic fields in special relativity. So this is now giving us a unified field theory in terms of the inertial field and the gravitational field. But again, as I stress, the interesting idea here is unification and not equivalence. As I said before, you wouldn't think of saying that the electric and magnetic fields is in some sense equivalent. I should mention, of course, that once you have this, if this is true in general relativity, which of course it is, test bodies do move along time-like geodesics, then you've explained something that was very mysterious in Newtonian mechanics. Because you've explained Galileo's law of free fall, universal free fall. The fact that bodies fall independent of their mass and constitution. Now, how do you get that in Newtonian mechanics? By assuming that the gravitational mass of a body is the same as its inertial mass. Now, there is absolutely no a priori reason why this should be the case. This looks like a little cosmic conspiracy. And of course, one of the things that one of the motivations in developing general relativity for Einstein was exactly to do away with this conspiracy. Of course, inertial mass and gravitational mass are not fundamental notions in general relativity, but when you go to the Newtonian limit, given this equation, you can show that when you describe the thing in Newtonian terms, the gravitational mass and the inertial mass must be the same. So, general relativity, by way of the geodesic equation of motion for a test body, is explaining or doing away with or resolving a particular kind of conspiracy in Newtonian mechanics. The question is, does it introduce any other conspiracies? Now, there's one thing, this is very, very clear, for example, in the paper that Einstein wrote in 1916, not his main review paper of the Einstein field equations, but a separate paper. And I think there's an expression here of a notion which I think is really very helpful. The introduction, says Einstein, of these labels, namely gravity and inertia, is in principle unnecessary. But for the time being, they do not seem worthless to me in order to ensure the continuity of thoughts. You don't really need to refer to gravity in general relativity. You've got the geodesic equation. You know how to define test bodies. You don't really need to refer to inertia, Newton's first law of inertia, because, again, you've got it out of the geodesic equation. Why introduce the terms at all? Well, Einstein says, if you want to have some kind of continuity of thought with the previous theories, you should be able to say in general relativity what corresponds to what we think is gravity, given our pre-general relativistic intuitions. Now, that may be useful under certain didactic circumstances, but it also may be very dangerous. And in a sense, the danger of using these terms is exactly the problem with the weak equivalence principle. The trouble is, of course, that if you try to teach general relativity or write a textbook on it, and you don't use the word gravity, you're in trouble. So here's one version of the weak equivalence principle. This is sometimes referred to as the principle of the universality of free fall. If a test body is placed at any initial event in space-time, and given an initial velocity there, and if the body subsequently moves freely, then its world line will be independent of its mass, internal structure, and composition. Now, free body, what does that mean, free body? Well, a free body means that there are no Newtonian, in inverted comma, forces acting on the body. For example, there are no electromagnetic forces acting on the body. The only force acting on the body is gravity. But gravity in general relativity is not a force. On the other hand, it's not a Newtonian force. On the other hand, this has to be true if you believe the geodesic principle. Because a test body is then being constrained to move along a geodesic, and the geodesic structure of space-time, that path structure in space-time, of course doesn't know anything about the constitution of the bodies. So this has to be true if the geodesic principle is true. Wouldn't it be nice if you could prove it? Well, this raises an interesting question in the foundations of general relativity theory. Most people say you can, some people say you can't. And I'll come back to that a little bit later. But in the standard formulation of general relativity, you certainly can prove the geodesic theorem if you lay your hands on the fact that the covariant divergence of the stress energy tensor vanishes. Sometimes referred to as the conservation principle. Something of a misnomer, but it's the conservation principle in general relativity. Divergence, the covariant divergence of T mean U, stress energy tensor vanishes. The question is, can you prove that by using Einstein's field equations? Well, the standard answer is yes, you can, because if you take the covariant divergence of the left-hand side of Einstein's field equations, that's the Einstein tensor, that vanishes identically. So the right-hand side of the Einstein's field equations, the covariant divergence of the right-hand side has to vanish, because these things are equal. The Einstein tensor is proportional to the stress energy tensor, therefore you get the conservation principle. That looks like a derivation. Not everybody accepts it as a derivation. It depends to some extent on how you formulate general relativity. But there is debate, particularly in the philosophical literature on space-time, about whether this is a proof or not. But let's keep an open mind about this. Let's assume there is at least a point of view according to which the geodesic principle, which underwrites this principle, is actually a theorem of Einstein's field equations. But a more standard account of the equivalence principle, the weak equivalence principle, is this one. And this is, I could have taken it from any number of textbooks. Einstein's equivalence principle is the idea that there is no experiment that can distinguish a uniform acceleration from a uniform gravitational field. The two are fully equivalent. And notice that Hartle puts equivalent in scare quotes. The big question here is, what does equivalent mean? Now, of course, there's this historical point that I've made that to say that this is Einstein's equivalence principle is really somewhat problematic, because Einstein really was interested in unification, not equivalence. But what does it mean to say that if you're experiencing, for example, if you're in a rocket ship and you're accelerating and you're going to experience inertial forces, that's exactly the same as being in a homogeneous gravitational field, a uniform gravitational field? Are we saying that the two things are one and the same thing? Are we saying that on the surface of Earth there is a homogeneous gravitational field and that we can simulate it by way of taking a rocket out to space where there are no gravitational fields? Well, gravity is not a force in general relativity. And really the problem here is that this notion of equivalence is really rather misstated. If you're accelerating with respect to the local inertial frames in general relativity, you will see effects. That is all that approximately homogeneous gravitational field is. In a sense, the important point here is reduction rather than equivalence. In general relativity, an approximately homogeneous gravitational field is just the effect of a Lagrangian accelerating with respect to the local inertial frames. You're not saying one thing is equivalent to the other. You're reducing gravity to an acceleration. Of course, there's more to gravity than just acceleration, because there are also inhomogeneous. There are cases when you can measure the inhomogeneity of the gravitational field. The closest appreciation of this point, that equivalence here, the word equivalence is really somewhat problematic, is in a very recent textbook I've come across that was published last year by Poisson and Clifford Will. Eric Poisson and Clifford Will. And here's the way they put it. Einstein's formulation is deeply flawed when taken literally. The strict adoption of his principle of equivalence has led to a pointless literature of apparent paradoxes, debates, and conundra. A uniform gravitational field is not a gravitational field at all. It is the field experienced by an observer undergoing constant acceleration in Minkowski spacetime and nothing else. Einstein's original formulation is not an equivalence but a tautology. And their gripe with this, with let's say the Hartle version of the weak equivalence principle, is essentially that there are no homogeneous gravitational fields in nature, which is true. Gravitational sources do not all the gravitational sources we know in the universe produce inhomogeneous gravitational fields. So their point is something like this. If you go back to Minkowski space-time, you can, as it were, simulate what you think is a gravitational field just by accelerating a uniform acceleration of the laboratory in Minkowski space-time. That will give what looks like a homogeneous gravitational field. But the problem here is, when Einstein introduced these notions, and when we look at the equivalence, the weak equivalence principle in general relativity, textbooks on general relativity, we are not talking about Minkowski spacetime. We're talking about real spacetime, which is curved. We're talking about general relativistic spacetime. The point here is that there are situations, and they're common. Most of the experiments we do on the surface of the Earth do not detect the curvature of spacetime. Insofar as they see a gravitational field, it's homogeneous, approximately homogeneous. And now the question is that inhomogeneous gravitational field simulated by some rocket that's, you can imagine, accelerating in space without any gravitational fields, and so we can use that calculation somehow? Or is what we call the inhomogeneous gravitational field just the result of an acceleration? And I would say that in general relativity it's the latter. So I think all of the sentiments here involved in the Poisson will critique hold just as well in general relativity. The fact that there are no strict homogeneous gravitational fields seems to me to be a red herring. So much for the weak equivalence principle. I want to cite some authorities here to remind ourselves the important role in understanding general relativity that special relativity plays, and particularly historically important role that special relativity played in Einstein's arrival at general relativity. So here's Einstein himself, 1916, the famous review paper, shortly after he discovered the field equations, for infinitesimally small four-dimensional regions. We would say for local patches of space-time. The theory of relativity in the restricted sense, special relativity, is appropriate if the coordinates are suitably chosen. These are what we now call the local Lorentz frames, if you like, the freely falling Lorentz frames. If a rigid body is imagined to be given as a unit measure, the coordinates have a direct physical meaning in the sense of the special theory of relativity. In the general case, when we are no longer able, by a suitable choice of coordinates, to apply the special theory of relativity to a finite region, that's to take extended patches of space-time, not these local patches, we shall hold fast to the view that the metric describes the gravitational field. So special relativity holds in these localized regions of space-time, essentially where we don't see curvature. But when we develop general relativity, we're going to hold on to the idea that we got in special relativity that because of the Lorentz covariance, the symmetry group in special relativity, we can talk about a four-dimensional metric with a Lorentzian signature. And we're going to keep that idea in general relativity. Here's Schrödinger. Now, those of you who have read Schrödinger's book, Space-Time Structure, will know that he starts his discussion of gravity by thinking purely in affine terms. He describes an affine connection. We know that you can define curvature in terms of the affine connection, and so on, before he gets to a metric notion of space-time. And he points out that an affine connection already gives rise to an invariant spatiotemporal interval, ds, along every geodesic. A geodesic is also an affine notion. It's the straightest curve between two events in space-time. Comparison of length or interval become possible. The idea suggests itself that this comparison of intervals should not be restricted to just one and the same geodesic. What you want is a notion of an interval that holds for all the geodesics, not just defined for one. The second circumstance is that an invariant interval is actually known in the so-called restricted theory of relativity. So when we talk about extending the idea of an interval across all the possible geodesics in space-time, we're doing this because we know something about the invariant interval in special relativity. And finally, this is Kip Thorne and Clifford Will in an article published in 1971. How do we know that special relativity is valid? The evidence for the metric field comes largely from elementary particle physics. It is of two types. First, experiments which measure space and time intervals directly. For example, measurements of the time dilation of the decay rates of unstable particles. These are famous twins type experiments. Second, experiments which reveal the fundamental role played by the Lorentz group in particle physics, including everyday high-precision verifications of form momentum conservation and the relativistic laws of kinematics. To cast out the metric tensor entirely would destroy the theoretical backing of such experiments. But these particle physics experiments, which are underlying special relativity, do not guarantee that there are global Lorentz frames. I mean, we know how to define inertial frames in special relativity. But none of these experiments are referring to very localized patches of space-time. We don't know that these inertial coordinate systems, suitably defined, can be extended indefinitely far out in space and time. In our case, of course, we know they can't be. Nor that freely flowing particles move along geodesics of the metric field along straight lines in the local Lorentz frames. In other words, none of the experiments that are underpinning special relativity are telling us what the inertial frames are. They don't rule out the possibility that the inertial frames are not, for example, more or less at rest in the surface of the Earth, which is the way Newton thought, and Einstein thought in 1905. Maybe they could be freely flowing frames. Maybe the inertial frames could be the freely flowing frames. And these experiments don't determine which is the case. So this is the sort of the opening into general relativity. But now there's a question I want to pose. The evidence for the metric field with the Lorentzian signature comes from the special relativity and buttressed by experiments in particle physics. Special relativity holds in regimes where gravity is negligible. And as we'll see in a moment, this is essentially the content of the strong equivalence principle. So why should gravity be associated with a metric with the Lorentzian signature? All of the evidence comes from special relativity that there is such a metric. And special relativity is valid in exactly those places where gravity doesn't exist or can't be seen. So why is it that gravity is picking up this metric structure? Now I know that this question is ambiguous, it could be read in a number of different ways, but I hope in the last comments of my talk I'll try to explain why this is something that I think is worth thinking about. Let's ask ourselves a very simple question. When you're learning special general relativity and you're looking at the Einstein field equations, and you know that these are equations that govern a metric field with a Lorentzian signature, a tensor field, let's ask ourselves, what are the operational aspects of this field? I mean, how do we go about measuring it? What does it mean operationally and so on? Well, we've already seen the geodesic motion of test bodies. So if you put a test body with a certain initial velocity into space-time, then its motion will be constrained by the local geodesic structure, which itself is determined by the metric field. James Anderson once remarked, the funny thing about general relativity is there are no free particles. We talk about freely falling. But freedom here is a restricted freedom. You've got to stick to the geodesics. Light rays trace out null geodesics. How do they know what to do? How does a photon know anything about this background null cone structure in space-time? Well, Eddington was the first to point out, you can't just assume this. You've got to prove it. And what you need to prove it are the Einstein-Maxwell's equations. You've got to know how the electromagnetic field couples to the metric field. You have to have equations. And in the end, you have to use the geometric optics approximation, and you have to show that light waves actually traverse the null geodesics. And this, again, is done in many of the textbooks. And this is the honest way. This is the honest way to understand why there's a connection between null light cones and light. Null cones and light. But finally, the one that's most interesting to us, rods and clocks. Rods and clocks, rigid rulers and clocks survey the metric field in general relativity. Particularly the case of clocks, chronometricity. chronometric significance. If you have a clock that's moving in some arbitrary way, not necessarily freely falling or inertial, and you mark two events on its world line, then in general relativity, it's claimed that if you integrate the little ds given by the metric along that path between the two endpoints, you're going to get a distance, and that distance is proportional to the proper time of the clock. The clock ticks in accordance with the background metric. How does the clock know what to do? Does the clock read the metric? The clock just does what it does. It ticks. Somewhere along the line, you've got to introduce matter fields. And you've got to have a model of a clock in terms of matter fields. The same with rigid bodies, the same with rigid rulers. This is not a question of definition. In fact, it's so much not a question of definition that if you think about an accelerating clock, as Eddington said, suppose you take a clock which is very, very, very accurate, like an atomic clock or something. When it's freely falling, it's moving inertially. So maybe it's sitting in a freely falling laboratory and it is incredibly accurate. That's to say it ticks in conformity with the temporal parameter in Schrödinger's equation. We know how to build these things. Now what happens if you accelerate it? Well, as Eddington said, if you take a clock and you accelerate it, you have to hit it. And hitting it isn't always a very good thing for clocks. So you have to introduce an assumption that the acceleration that you're producing, the forces that you need on the clock to accelerate it, are very much smaller than the forces of cohesion inside the clock for this thing to be true. And in general, it's false. You can always find an acceleration for any given clock that will make it not satisfy this chronometricity assumption. But fortunately, we have tons of clocks around us, particularly things like elementary particles and their decay rates, which are pretty good under accelerations. So we're okay. But we can't take this sort of thing for granted. It's not a question of definition or luck. It's a question of dynamics. So what do we have to say? We have to have a model of these clocks. We have to have a model of these clocks. Incidentally, a wonderful paper that was published in the 1980s showed that a muon decay, remember muons were used to measure time dilation, special relativity, moving muons very, very fast, relativistic muons, that of course they were accelerating because they were they were in the CERN, what's the term? Accelerator. Circular accelerator. They were suffering accelerations of 10 to the 18 G. And there was a beautiful paper by a man called Eisel who showed, using the theory of the weak interactions, actually modeled the decay of elementary particles and showed that 10 to the 18 G is okay. But if you were to put the same muon in a magnetic field close to a radio pulsar, for example, where they have very, very intense magnetic fields, you could really affect, you could make it, you could see measurable deviations from the so-called clock hypothesis. Good. So I'm going to say none of these operational aspects of the field of the metric field in general relativity follow from the field equations. None. You have to have something else put in. In the case of the geodesic motion, I was arguing before that there is a theorem, it's often called the geodesic theorem, where you use the field equations to show that you have conservation of the stress energy tensor, and that's enough to give you, if there are always difficulties about defining rigorously test particles, but there are some nice proofs, particularly by Robert Garrosh, that give you the geodesic motion. But all of these proofs require something a little bit over and above the field equations. They require the dominant energy, strength and dominant energy condition, which is essentially telling you that the flow of energy is always subluminal, luminal or subluminal. That's not a consequence of the field equations. So this is very close to being a consequence of the field equations, at least commonly thought. Not quite. Well, this one, as I say, requires knowledge of what's sometimes called the Einstein-Maxwell equations, and of course you have to have a quantum version of that eventually. But what about this one? Rods and clocks. They're matter fields.
Could I just ask, you say consequence of Einstein-Maxwell.
Yeah.
But if you just take the Maxwell equations in every local patch and you show that the light goes at the speed of light, can't you just patch all those local patches together and say, therefore, it must be a null geodesic?
Yeah. But how do you know from the field equations that Maxwell's equations are valid? You can't derive Maxwell's equations from Einstein's field equations.
No. No, but I'm just the other way around. I'm just saying, if you only had Maxwell's equations, but you knew that they were valid in every local patch, wouldn't that tell you globally?
How do you know they're valid in every local patch?
Well, I'm just assuming.
Okay, but that's exactly what I'm coming on to. Well, I've said something about the geodesic theorem, but I'd like to go on to exactly this issue of rods and clocks. This is what the strong equivalence principle in general relativity is designed to do. Here's Misselthorne and Wheeler. In any and every local Lorentz frame, anywhere at any time in the universe, all the non-gravitational laws of physics, the ones that account for the existence of rods and clocks, because they're matter fields, must take on their familiar special relativistic forms. Here's Ohanian in 1975. At each point of space-time, it is possible to find a coordinate transformation such that the gravitational field variables can be eliminated from the field equations of matter. Remember, special relativity, there's no indication of anything like a curvature tensor or a curvature scalar. This is Giulini in a very nice paper on how you test for the equivalence principles in general relativity using quantum mechanics. With reference to freely falling frames, the non-gravitational laws of physics are those known from special relativity. You're putting the local validity of special relativity in by hand. It's not a consequence of the field equations. How does this work? There are really two aspects of this assumption. This is a point that was stressed by James Anderson in his wonderful book on general relativity. First, what might be called universality. What's a local freely falling, what's a local inertial frame? Define an event in space-time, put a coordinate system around that event. At the event in question, the first derivatives of the metric will vanish, so the connection coefficients will vanish, and you can diagonalize the metric to make it look like the Minkowski metric. It will be in diagonal form. That's a freely falling local Lorentz frame.
Is the word event ever actually defined in that context? I mean, in the sense that if you were observing, like as you were saying, you would actually do basically a measurement. In other words, you put a screen there and observe it, so the wave function would collapse or whatever you want to describe that process. Is that, I don't necessarily mean wave function collapsing, but I mean in essence, is that what we're talking about in an event? You actually observe something?
No.
So how does the word
Well,
event
first of all,
actually,
first of
that's
all,
always confusing.
Yeah. In general relativity, first of all, this is not a quantum field. We're talking
No, I agree, but I was just...
okay, but I think one way to understand is, don't understand it, for example, as a point in the space-time manifold, because that's just a mathematical argument. Think of it perhaps as, you've got a series of fields, tensor fields, for example, in space-time. You've got the metric field, you've got the matter fields, and so on. Think of a location where you can specify the values of all these fields instantaneously, the components of all of these tensor fields. That's going to define an event. It's localized, it's instantaneous, and it's picking out an event. There may be a better definition, but I don't know it. Maybe we could come back to this.
Yeah, sure.
So you've got an event, you've defined a coordinate system associated with that event, not just on the point, of course. It extends out into space-time. But at that very point, the coefficients of the connection vanish, and the metric becomes diagonal. With respect to those coordinate systems, and remember they must be related by a Lorentz transformation, because in all of these coordinate systems there's an infinity of them, you're diagonalizing the metric. And the only way you can do that, to go from a diagonal metric to a diagonal metric, is by having a Lorentz transformation. And what we're assuming is, if you take the equations for the material, the matter fields, like the electromagnetic field, we're going to assume they all take their simplified form in those coordinate systems at that point. all of them. Strong force, weak force, electromagnetism. They all take their simplified form in these local freely flowing coordinate systems. That's a miracle. Why is it a miracle? Because we don't know how to unify these forces. Why should they all become simplified in the same coordinate systems? And incidentally, so there is a kind of a conspiracy that's introduced here, which is already implicit in special relativity, of course. Why are all the fundamental matter interactions, non-gravitational interactions, Lorentz covariant, with respect to the same coordinate systems? Why is that? We don't know. Good. However, I mentioned, for example, that since the claim is that you get the simplification of the laws with respect to all of the local Lorentz frames defined with respect to a particular event, that rules out the introduction of something like a vector field, which might violate the relativity principle. Mattingly, Jacobson and Mattingly, I think it was in 2001, introduced a theory in general relativity where you get a violation of local Lorentz covariance on the part of the matter fields. But to do that, you need to introduce a vector field in spacetime, a dynamical vector field, which picks out a privileged state of rest. You're violating the relativity principle, after all. And this assumption here is ruling that out. This universality assumption is ruling out the possibility of a violation of the relativity principle, and therefore local Lorentz invariance. That's enough to establish special relativity. What is special relativity, by the way? Here's the mature Einstein, 1940. The content of the restricted theory of special relativity can accordingly be summarized in one sentence. All natural laws must be so conditioned that they are covariant with respect to Lorentz transformations. He's moved away from the 1905 formulation of special relativity where he talked about the relativity principle, the light postulate, and he says, no. I set up that way of doing special relativity on the basis of a thermodynamic template. Let's be more detailed about this. Lorentz covariance is the heart of special relativity. That's the heart of special relativity. Special relativity does not give you Maxwell's equations. It just tells you whatever the equations of the electromagnetic field are, they have to be Lorentz covariant. So it's a constraint on the possible dynamics, but it doesn't determine the dynamics. So here we have a universality condition that's giving us local Lorentz covariance for the matter fields. But now we go even further. We go beyond special relativity. And we simply say minimal coupling. What does minimal coupling mean? It just means we have been successful in understanding the non-gravitational interactions in special relativity, where we didn't see any sign of curvature. We've been successful with things like Maxwell's equations for classical electromagnetic fields and so on and so forth. They better be incorporated. Those equations better reappear in general relativity. Those equations are better reappear. This is stronger than imposing special relativity because you're actually specifying the form of the equations now. Minimal coupling just means when you, at that event where you've got these local inertial coordinate systems, at that event, the field equations look just like they do in special relativity. Except that they don't. They almost do. There's a caveat that's often forgotten in the textbooks. If they're first order equations like Maxwell's equations for the electromagnetic fields, all you do is you replace the commas, the derivatives, by covariant derivatives. Commas go to semicolons. And that's well defined and it works. But it's ambiguous in the case of second order equations. And at any rate, if you take Maxwell's equations and you look at the wave equation for F mu nu, that's a second order equation. And there, in general relativity, you automatically pick up curvature terms. So this idea that the non-gravitational laws of physics are those from special relativity only applies to first order equations. First order equations. Well, I'm going to finish up now. What I'm really trying to say here is, if we want to try to understand why rods and clocks have any connection with the background metric in general relativity, the solution of Einstein's field equations, rods and clocks are not thermometers of spacetime. They don't feel spacetime. There's no interaction between the spacetime and the rods and clocks per se. However, if the matter field equations, out of which rods and clocks are built, satisfy these assumptions, then the rods and the clocks will have some connection with that background metric that's already assumed in Einstein's field equations. None of this comes out of the field equations themselves. And there's a kind of what might be called a double conspiracy here. We've seen that general relativity removes one conspiracy. It tells us why, using Newtonian language, inertial mass and gravitational mass are proportional. That's great. But now we've had to introduce an assumption, or a series of assumptions, over and above Einstein's field equations in general relativity. One is that all the non-gravitational interactions have this joint symmetry, and that's surely non-trivial. And second, that they're Lorentz covariant. I mean, in other words, we're ruling out something like this Jacobson-Mattingly theory where a vector field exists that violates the relativity principle. In other words, what we're doing is we're saying that the matter fields are locally Lorentz covariant, and that means, just as we learned through Einstein's original work, that there's a metric, an emergent metric associated with those equations, which has the Lorentzian signature. And it just so happens to match the Lorentzian signature that was already there in Einstein's field equations. Doesn't that look a little bit conspiratorial? Why is the signature appearing twice in general relativity? Well, I could say more. I think there's a possible way, and it depends on whether or not the geodesic theorem is a theorem. But it would take a little bit longer to explain. But I think these issues, the issue of the local validity of special relativity and general relativity is a very subtle business and very interesting. And without it, one has no understanding as to why rods and clocks play the role they do in general relativity. Happy birthday.
Okay. Roger.
I'm a little bit surprised in a way that you put rods and clocks in the same bracket, because there's a very big difference. I mean, clocks measure lengths of road lines, whereas rods don't. I mean, a rod is something it doesn't actually measure the distance between the two space-like separated points. You've got to worry about the motion of the rod and so on. So it's a more complicated structure. And moreover, in actual practice, clocks are ridiculously more accurately measured. I mean, we have atomic clocks, nuclear clocks, and so on. Whereas the meter rod in Paris is pretty well useless. The length of it is determined in terms of light, how long it takes light to go up and longer and so on. So it seems to me that fundamentally they have a very, very different character.
I think that's right. But coming back to your point about their relative precise use, very, very accurate clocks are a very, very recent thing in history of physics.
That's true. Yeah.
Up until the end of the 19th century, the most accurate clock was the rotation of the Earth. Not something you can carry around with you. No other movable clock was anything like as accurate as the rotation of the Earth. It was really only in the 20th century with atomic clocks that we got closer to, and now with pulsars and so on. And yet, for centuries and centuries and centuries, for virtually the length of human existence, we've had objects that are pretty good rulers.
Yeah, I think
in other words, rigidity is ubiquitous. Reasonably accurate rigidity, reasonably good rigidity is pretty ubiquitous, but very accurate clocks are a very recent thing.
Well, you could always use the speed of light to act. I mean, if the rod is good, then you get a good clock already. But I think in a way the point is not so much that, which, I was making that point. Right. And I think that fundamentally, the way you think about how the metric is measured and so on, it's really clocks. The lengths are secondary. Now you have to think of what's simultaneous, and then you have to reflect light signals and all that.
That's right.
So they really, once you've got the clocks and the light signals, you've really got everything.
Okay.
But I think it's still the case that, I mean, even if you do make a distinction between rods and clocks, there is a question as to why the clock does what it does.
Well, that's another point. Yes.
And there you have to model it.
Yeah, and I think your point is right. If you have a clock, mechanical clock or something, you might worry about whether the acceleration is going to affect it. It probably will.
But even in the absence of acceleration, there's the question as to why, for example, an inertially moving clock dilates.
Yes, well, this is the theory. There are a lot of wires you can put in there.
Yes.
John?
So this point you made about AV term in Maxwell's equations.
Say again, sorry?
The point you made about the vector potentials in Maxwell's equations, the dynamic of the photon. So you seem to be saying that, maybe I misunderstood, but you seem to be saying that the covariant derivative is okay because it's first order, and therefore if you've gone to a local flat space, then that's okay. But so now the dynamical part of Maxwell's equations, which the AV term, AU term is not. But I mean, at least in quantum language now, then they're all just coming from the same source, which is the imposition of local gauging theories. So how can they really be different in their sensitivities to
I wasn't talking about the Maxwell's equations for the flow vector potential. I was saying if you take Maxwell's equations for the E and the B fields, those equations are first order.
Yeah.
The minimum coupling procedure is well defined. Okay, we know how to write down Einstein-Maxwell's equations exactly the way that I mentioned before. We use the minimum coupling procedure. We know how to do that. But when we say that all of the local physics in general relativity is the same as in special relativity, we're exaggerating. Because if we look, for example, at the derivative of the Maxwell tensor, which is like a wave equation, okay, there, in general relativity, that equation picks up terms that depend on the metric, on the curvature.
That was my question. I said,
Right.
so that may well be true, but both within the language of QED, they're both coming from the same source.
Oh, absolutely.
With local gauging variance. And if that works, I mean, are you saying that having a U1 gauging variance in some auxiliary space has to couple with the metric, but in a way that we don't really understand? Am I completely bad?
No, I'm just saying
It
that...
seems odd to me that the two could have different problems associated with them when they're coming from the same source.
I mean, you're raising a couple of questions. One is, to what extent QED or Maxwell's equations are the direct result of imposing a UN gauge symmetry? That's an interesting question in and of itself. I don't think it's an obvious fact that Maxwell's equations are given just by gauge considerations. However, the point that I was simply trying to make is, in general relativity, when we know we have successful equations in special relativity for the matter-field interactions, of course we want to incorporate them in general relativity. After all, general relativity is more fundamental. I mean, that's where they really are. Special relativity is only really a kind of limiting case. So they've got to be there in general relativity. And I'm just saying, this ansatz that we use, sort of historically going from special relativity into general relativity in terms of these equations for the matter fields, which is the minimum coupling procedure, gives us, in the case of electrodynamics, equations, the first order equations look just like they do in special relativity, but not the second order equations. So this claim earlier that you see all the time, we can, in general relativity, we can transform gravity away locally. Well, it depends on what you're doing, and it depends on what equations you're looking at. In the second order equations, you cannot transform.
You already have the issue with the wave equation for scalar.
Yes.
You put the
Yes.
conforming version of
That's right. That's right. As long as the equation's in second order.
Anybody else? No? Well, thank Harvey again.